Did you get a message? I didn't get any message. Is the recording started now? It says it started. Hopefully you got a message.
Yeah, I got a message.
Okay, great. Okay, so I'll just simplify notation a little bit. So recall what we did. I mean, I'll just do a little bit of a discussion and then kind of give you some intuition and then give you some kind of geometric picture and then indicate certain things and then go to quantum compression. So it's not going to be like a very proof heavy class. Okay, so recall, so we had this, right? So sigma is essentially px of x rho x. So really in the classical world, this is like py, this is like py given x, and this is the averaging px of x. So this is kind of what it is. So I will just do the following. I will define I'll define a system. So I'll define a system gamma, not a big deal. Gamma, I define it as follows. So it's a classical quantum system. So this is a density operator, but it has two components. So I will call it system y and x, okay, or let's say x and y. X and y, gamma xy. So it has two components. And just like we say pxy, right? It has two classical registers. Just like that, I'm going to talk about just like this, I am talking about gamma xy. So it has a classical register and a quantum register, just a joint state. What is this joint state? It is defined as px of x outer product x tensor rho x. So with probability x, the state of the system is this. That is, if there is x in this register, the quantum register is in state rho x. If this is in state x tilde, the quantum register is in state rho x tilde. And the probability that it will be in this pair of states is px of x. So that's really what it is. So it's a two-component system. It is usually referred to as a classical quantum system. So I mean, this will just help us write things simpler. So gamma xy, I'm just writing this once again, just for px of x, outer product xx, tensor rho x. So let's compute the marginals, right? So gamma x, just as we would compute the marginal px and py. So let's compute the marginal. Gamma x is, you trace out on y, gamma xy, and you will see that you will get px of x. So this is the state of the classical register. Gamma y is trace over x of gamma xy. So this is so you're going to get px of x rho x. That's the state of the classical quantum register. So in an average, so it's in state rho x with probability px. That's what it is. So I can talk of, so I will say S of x is the trace of, the entropy of the classical part. So gamma x. Okay. So S of y, S of gamma y. Okay. And S of x comma y is S of gamma xy, right? So now what we are saying, so now recall, so yesterday, so we were doing this, right? So sigma is summation px of x rho x. So I can write gamma y as sigma, gamma x as px of x, xx. And if you see what traits we got S of sigma minus Px of x, S of rho x. So this really, I mean, if you recall, if I have a two-component quantum system, so suppose I have a two-component quantum system theta AB, then you recall I defined S of A given B as S of A comma B minus S of B. Now let's go to gamma xy. So what is so let's go to gamma xy. What is S of xy? S of xy is S of this thing, Px of x, x tensor rho x. And this we observed. So this is S of xy. What did I want to do here? So what is S of okay. So I claim this is the following. I claim this is h of px plus px of x S of rho x. Do you agree?
Yeah,
And the reasoning?
like all of them are orthogonal because you had the x's.
Yeah, if you think of this as alpha x, then alpha x's are all orthogonal because you have put a tail which are orthogonal. So so hence it is just um, it is just the entropy of h of px times so when they're orthogonal, you will actually get the distribution of this plus px of x s of so this is
Yeah,
essentially
yeah. Like what I'm saying is,
h
because
of
in orthogonal, it will be h of px plus summation of px s of x tensor rho x.
yeah
But that is the same as
that is
s of.
same. Okay, so that is same as this. So s of xy is the above quantity. What is s of x? What is s of x? S of x is h of px. S of y is s of summation px of x rho x. So what is h of s of y minus s of y given x? So this is essentially s of y minus s of y comma x plus s of x. So this is so I'm going to write everything h of sorry, so this is this s of px of x rho x minus h of px minus x px of x s of rho x plus h of px. So this component is here by just by the fact that this is this. Then this component is this plus this that comes from here, which came from here. And finally, this s of x is essentially this. So I get s of y. So I get exactly what we got yesterday. So I'm just writing px of x minus px of x s of rho x. So this is the so you can look at the CQ channel also in this form. So if you are given the CQ channel, you can write the CQ channel as follows: px of x times x is the rho x. Then your capacity is essentially s of. So if you call this gamma xy, your capacity is essentially s of y minus h of y given x. And when you want to cover, you just go about that. Okay. Okay. So so I will now give you a little bit of intuition on this covering lemma. So I was kind of stating this that day when I was discussing with Tejas, so I'll just kind of elaborate a little bit. So go back to the classical. So what is the scenario? So let us just fix some arbitrary x and y and pxy. So pxy. So px denotes its marginal, py denotes its other marginal, py given x denotes its conditional. Let's just fix this. Just take an arbitrary thing and fix it. So let this be the typical set of px. So xn is a big set, but t delta n of px is the set. Let this be the typical set of y. So there are all these points here. These are all the typical xn's. There are 2 power n h of x number of them. So if you forget the y, you just completely forget the y, each of these points is essentially picked uniformly at random. As n becomes large, nature is just picking these guys uniformly at random. Now, similarly, if you look on the right side, there is 2 power n h of y number of sequences. If you forget the x, nature is just picking them uniformly at random. Okay. Now, if nature has picked a particular xn, so just 1 second before I go there. So each fellow here has a mass of 2 power minus n h of y. Each mass here has 2 power minus n h of x. I'm going to give one more picture at the bottom. So I'm going to put all the xn sequences on the left and all the yn sequences on the right as a line. Okay. So this is 2 power n h of y. This is 2 power n h of x. Now, if you pick a particular xn, then the corresponding yn, so if nature has chosen this blue xn, then nature will also choose a yn in a particular ball uniformly likely. So there are 2 power n. So this ball has size 2 power n h of y given x, and each one of them is picked uniformly at random. Similarly, if I take another one, this will also come out randomly 2 power n h of y given x. So you take another one and so on. So essentially what is happening? So each fellow here, the corresponding ball is coming out uniformly at random. Now, if you wait large enough, what is happening? These left colored sequences are picked uniformly, and conditioned on one of them being picked, the sequences in the right corresponding colored ball is being picked uniformly at random. And it so happens that if you forget the x, it's as though all these balls are uniformly averaged, right? Each ball is picked uniformly because each point on the left is picked uniformly. So each ball on the right is kind of picked uniformly, and within that ball, each point is picked uniformly whenever that ball is chosen, and it all kind of nicely adds up, and you will see that the entire collection of yn sequences are kind of uniformly at 2 power minus n h of y. Now, so there is this critical number. So there is this critical number I of x colon y. And what happens if you pick slightly smaller than I of xy number of sequences, then all the balls on the right are disjoint. So you just randomly pick 2 power n I of x colon y sequences on the left, and so it's a random collection, and with very high probability, extremely high probability, probability on your choice, right? You picked something, right? Today you picked something, it has a particular footprint on the right, right? This you picked something else, it has a different footprint on the right. Now you picked something, and with very high probability, those footprints are completely disjoint on the right. If the exponent of your picking happens to be less than I of x colon y. Now, so if you do this thing, right? So what you do today, you wake up and you pick 2 power n I of xy number of I of xy minus delta number of sequences. Pick them, you fix them, you just fix them, and from tomorrow you start uniformly picking from this collection. So you've chosen a collection. Today you just woke up and you chose a collection, then you sit with that collection for the rest of your life, and if you uniformly pick from that collection, the distribution on the right is not going to be like py. It is not going to be uniform on the typical set. It is going to have blobs that are disjoint. Okay, that's very important to understand. So when you are operating in the realm of the packing lemma, the blobs are all disjoint. So you're picking uniformly from these balls. It is no way related to the distribution py. Okay, so they are quite different. So here it completely concentrates, and it looks away from the py. The py is very smooth. It's completely smooth. There are no holes, there are no gaps, there are no edges. The moment you pick more than 2 power n I of xy number of balls, right? It is as though you've kind of filled up your entire space on the yn on the typical set of yn. So these guys not only just overlap, but they overlap, they are disjoint, and it turns out that you're picking each typical hy point is reached, and also reached at the right optimal level, so that the distribution is just uniform on the typical set of py. And because picking uniformly from the typical set of y is kind of essentially the distribution py, these distributions are kind of close. So that's what's really happening in the covering lemma. So the moment you go above this I of x colon y, you see this transition. So it's a sharp transition from a distribution that is, see, the point is the following, right? If you are operating in this regime, right, there is memory in the system, in the sense you can look at yn and you can tell which xn it is. There is kind of a memory in the system. So if you keep waiting for your yn sequences, if you are in this ball, you will know you'll end up in this ball, right? But the moment you go above I of x colon y, you're kind of completely randomly distributed. So that kind of memory is lost, and it's it's like as though you're just picking from py. So that's kind of the key point with this. So you see a sharp transition happening. The distribution before I of x colon y is kind of concentrated on blocks without intersections, and the distribution after you pick 2 power n I of x colon y sequences, they are completely spread all over the area. And the same thing happens now in the quantum thing, with essentially subspaces being replaced by these kind of balls, and either the subspaces are orthogonal or they kind of just overlap as though it fills up the entire space. Okay, I'll just kind of pause for questions, thoughts, comments. Maybe I should make this point. I will write this bipartite graph on the left. Okay, so there are 2 power n h of x sequences on the left, 2 power n h of y sequences on the right. So each point here on the left has an out degree of 2 power n h of y given x. This is the out degree. Now they are all overlapping. This bipartite graphs, the kind of the fan outs of all these guys are overlapping. If you look at the in degree at a point on the y on a yn point, right? It is 2 power n h of x given y. The total number of edges is 2 power n h of x comma y. Okay. And this is kind of a bipartite graph. And what you are doing is you don't have to pick all of them to reach all the points here uniformly. You don't have to pick everybody here. You can just pick 2 power n I of x colon y number of sequences. That's what is happening. And if you pick slightly less, you will fall in disjoint balls on the right. If you pick slightly more, they will all sit very nicely and give you that, complete tessellation. Okay, thoughts, comments?
So how do you know that the edges are 2:n h of x comma y?
Yeah. So I am connecting I write an edge between two vertices if they are jointly typical. Maybe I should have said that.
Oh.
So a yn is connected to an xn if x and yn is jointly typical. Now you look at a yn. So the in degree, the inside edges, the incoming edges are all those xn's that are typical with the yn, and that's 2 power n h of x given y.
Oh, so all the conditional typical xn's with respect to that fixed yn will be incoming to that yn.
Correct.
Okay.
And what nature is doing, okay, so maybe I'll make this figure slightly better. So something like this. Okay, so I'm going to write maybe yeah, maybe I'll do this. So maybe I'll do this. So there are 6 here on the right, and there is 4 on the right, and 6 on the left, and I'll have total of 12 edges. Okay, so that means the outside degree, so it's something like this. So I'll have 12 edges. So left side degree is 2, right side degree is 3. Okay, so it's something like this. You see what I'm doing, right? Essentially. Oh, I should have got the, okay. So I made a mistake here. I made a mistake. So if you see this graph, right? So I have 2 power n h of x sequences on the left, that is 6. I have 2 power n h of y sequences on the right, which is 4. So 2 power n h of xy is 12. The outside 2 power n h of y given x is 2, and 2 power n h of x given y is 3. So the outside, the left degree is 2, the right degree is 3. And what is nature doing? Nature is just, you forget everything. Nature is just uniformly picking the edges. That's all nature is doing. And what you end up seeing on the left, it's going to be uniform on the left, it's going to be uniform on the right. This is kind of what's happening. So when you pick a particular point, the edges from that are going to come uniformly at random. This is kind of your typicality graph. Does it make sense?
Yeah.
Yeah. Okay. Okay, great. So now I'll slowly move over to the next part. So hopefully the quantum covering lemma and all of that is now clear. The packing lemma and the covering lemma, why it happens, what is the intuition, everything should be making a lot of sense now. So now I'll go into quantum measurement. So I'll do an application of packing lemma. Application of covering, sorry. So we did an application of packing lemma, which was essentially the capacity of the CQ channel. Now I'll do an application of the covering lemma. And the problem is the following. So I will do, so this is quantum measurement compression. And the broad question is, how much information is contained in the outcome of a quantum measurement? So I'll give you some prelude to this. See, so quantum state, right? Our only window to the quantum state is essentially via a measurement. There is no other, absolutely no other. If somebody has, if somebody says I've prepared a quantum state row, I can't go check it. The only way I can check it is you make a measurement. So you design, you sit today and you design a measurement lambda k. Now, if he claims he has designed a quantum state, if somebody claims that he has designed a quantum state, he has designed a subatomic particle in state rho, you can't verify it. There's no way to verify. The only way you can verify is, okay, you design a measurement whose specification is still lambda k, and you perform measurements on this. So you perform, say 100 measurements, and when you make 100 measurements, if you get the outcome k with proper, so you're gonna make 100 measurements, and you're gonna say tabulate how many times I will get. Now let me take my capital K to be say 10. So I have 10 operators in my measurement, and what I will do, so I make 100 measurements and I will count, okay, how many times did I get 1, how many counts, how many times did I get 2, and how many times did I get the outcome 10. And if for each k, the number of outcomes I get k happens to be close to trace lambda k rho, then I have a sense of belief that possibly he has prepared a quantum state rho. So there's absolutely no way to tell whether he is, so it's a completely blind world. So our entire window into a quantum state is through a quantum measurement. So quantum measurement is a critical element in anything you do in quantum. And the question we ask.
Sorry, I just have one question.
Yeah.
Sorry.
Yeah.
So if you have this distribution, trace of lambda k rho,
Yeah.
then can we know rho uniquely if we just
No.
know this distribution?
No, what you should do is you should take multiple measurements. So you should take lambda k, and you should take another theta k, and for all of them the distributions have to be consistent with what you expect.
Oh, so we need many POVMs, you're saying?
Yes, correct. Think of the following. Okay, it's like this. I'll give you an exact analogy. Suppose somebody tells you that he has placed a sample in a classical register, and that sample is distributed according to px. Okay. you suppose you can't see the classical register, but you can only apply some function to it and you can get the function outcome. Okay, that's all you have. You're not you do not have access to the register. So there's kind of a wall here, and this is the register here, and somebody claims he has put a data in this register with distribution px. You can't see behind this wall, but you can poll with some function f. Give me the value of this. Give me the function value applied on this data register, and they will throw out a value. Now, how do you check whether this distribution is indeed px? Well, if you just take one function, it's not going to work. You have to take, kind of an exhaustive collection of functions. And if for this entire exhaustive collection, so what you do when you do function x, you will actually look at this, right? So you will actually look at the distribution of f of x. And if that distribution is what you would get if this was indeed px, and this was true for all functions f, then you can be fairly confident that the data he has put is indeed according to distribution px. Do you understand?
So if f was 1 to 1,
Yeah,
then you would just need one function.
correct. That is true. If f was 1 to 1,
Okay.
can you get such a thing with measurements? You can. So you are designing a function, a good function, right? So here, if I take my measurement to be orthogonal and completely projective, so complete orthogonal projective measurements will give you some sense, right?
Okay.
So that's the that's kind of exactly like that. Okay, cool. So the outcome of a measurement is really the only window into our quantum state, and the question is, how informative is this outcome, right? If the information content of the outcome is not good, then essentially the measurement is not of much use, right? So that's really the question we are trying to ask here. How much information is contained in the outcome of a quantum measurement? So this is the question I will ask. So so what happens when you make a measurement? So suppose I take a quantum state rho, right? And I make a measurement. Let's say I'm taking a POVM. I'll explain this POVM setup a little bit later. So I take a POVM lambda k. Let's say I take a non-POVM. So general measurement. I take a general measurement mk. So I have capital K number of outcomes. I take a measurement mk. What happens? This quantum state will go to mk rho mk dagger divided by trace mk rho mk dagger. So let me call this theta k, right? If my classical register ends up in state k, right? And the probability that will end up in this, so what is happening when I make this measurement? I'm ending up with a quantum state theta k, and I'm ending up with a classical register k, and this setup I will get with probability trace mk rho mk dagger, right? So essentially, what is my post measurement state? My post measurement state, so I have a classical part and a quantum part, and then there is a probability associated with this. Remember, this is very similar to your classical quantum state that I talked about. I talked about px of x, classical register in state x, and quantum state in register rho x, right? That's exactly what I'll get here. So I'm going to get trace mk rho mk dagger, kk, this is the classical part, and this is the quantum part. So alternatively, I can write this as, I will just write P of k, that's your probability. kk tensor theta k. Okay. So what is the measurement doing? So initially I had a classical register and a quantum state, right? But these were uncoupled in some sense. These were completely uncoupled. So I had some arbitrary distribution. I had some arbitrary distribution of the classical register. I had some arbitrary distribution of the classical register, tensor rho. Okay. So the quantum state was in rho. There was some arbitrary distribution. When I applied this measurement, I ended up in this. So maybe I should use K. When I do this measurement, there is a coupling that is built between the classical register and the quantum register, and I end up in this state. So this is very important to understand. So it's KK tensor theta K. So this is critical. So there is a relationship that's built between the classical register and the quantum state. And it is this relationship that is giving us information about the quantum state. See, previously there was absolutely no relation between the classical register and the quantum state. When you perform this measurement, you're tagging along something into the register. So the register is now informed about the quantum state, right? Now, the question is how much information is contained in this relationship. That's really so if these, see here on the left, right, there is absolutely no information content of the quantum register in the classical register. But on the right, there is some information content of the quantum register in the classical register. So this measurement, what it has brought about is it has brought about this relationship between the quantum register and the classical register. Now, any process that brings about the same relationship is essentially simulating the measurement, right? So any process.
Sir,
Yeah.
sir, can you please
let me write this down and then I'll take it.
Okay.
Any process that can simulate exactly the same relationship has essentially simulated the measurement process. Yeah, tell me, Srinidhi.
Sir, can you repeat the comparison you did regarding the information contained in both of the?
Yeah, see, previously, right, your quantum state, you prepared it in some state rho, and you had a dummy classical register with you, and there was no relationship between the classical register and the quantum register. Okay, there was absolutely no relationship. The left side could be in whatever state it wish, you put it in. The right was in the state rho. When you make the measurement, the outcome of the measurement now is stored in your classical register. That's your kind of your dummy register in which you're trying to store your outcome of the quantum register. So post measurement, there is a relationship established between the post measurement quantum state and the classical register. See, this is similar to a situation where, suppose, Alice is observing X and Bob is observing Y. Okay. Now, suppose there is absolutely no relationship between X and Y, right? They're completely independent. So, X observes something, Y observes something. As against to, they are, there is some relationship between what Alice observes and Bob observes, right? So that's exactly what is kind of built into the second system. So in the second system, Alice has some information about the quantum state. But in the first system, Alice has no information on the quantum state. So this measurement process brings about this relationship between the classical register and the quantum register. And hence, information about the quantum state has been now kind of, put onto the classical register. Do you understand?
Yes.
If this relationship were not there, there is no there is no information that the classical register contains about the quantum state. It's like, if the quantum register is in this state, my classical register is in this state. If my quantum register is in that state, my classical register is in that state. Means there is some. So this guy contains some information. So looking at K, you can tell, okay, what is the state of the quantum register? But on the left, if you look at K, you have no clue what the quantum register is. So that's what the
Yeah.
measurement process brings about.
So this is because like we perform measurement using the lambda K.
Correct. There is a
Yeah.
measuring process lambda K. And this P of K is essentially traced, not lambda K, I'm using MK. I'm using MK. So let's just kind of stick to MK as of now. And this P of K is essentially trace MK rho MK dagger. And now I will say the following. Suppose
Sorry, just one thing. Sorry.
Yeah.
So theta k will be mk rho mk dagger.
Yeah, theta k will be MK rho
Okay.
MK dagger divided by trace MK rho MK dagger. So it's a state.
Oh, you are also dividing. Okay.
Yeah. So it's like this, right? I'm writing. So if you want in the classical world, right? It's like this. I'm writing the distribution Pxy of x comma y as something like this. I'm writing it as x, Px of x, tensor Py given x of y given x, y. I'm kind of writing it like this. So this is like your, so this, yeah. So this is your k tensor, theta k. Theta k is like your Py given x. Just like your rho x was your Py given x, right? It's exactly like that. So for each, if you fix an x, this is a density operator on Py on space y. So if you fix k, theta k is a density operator. So theta k is mk rho mk dagger divided by trace mk rho mk dagger. Is this okay?
Okay, so just as how py given x is normalized, you're also normalizing that mk rho mk dagger.
Exactly.
Okay.
And there is that relationship that is built in, right? That's the key. The relationship has been built in. If Py given x was equal to Py, then they are independent. So if theta k was just invariant with k, then they are independent and x has no relationship to y and x conveys no information about y. That's the point. Because Py given x depends on that conditioning x, there is a relationship that is built in. Okay, great. So I will go back here to this picture. So I did the MK process, I mean the measurement process, and this induced this distribution. Now suppose, forget the MK process. If I can simulate this transition, okay, so let's understand this. This is important. So if I can simulate maybe this was the better picture. So I'll just stick to that picture. So if you understand this, then you pretty much understood the formulation. So suppose I have a pre-process classical register and quantum state. In this state, I do some magic operation. Not a measurement operation anymore, some magic operation. And I end up with P of K tensor theta k, where theta k is mk rho mk dagger. I don't do MK, but I end up in this state, suppose. And P of K is trace MK row, MK dagger. Then this magic process, magic operation gives me the same amount of information as the measurement process. Do you agree? This is very important. So I'm going to write this question. The magic operation gives me exactly the same amount Do you agree?
Sir, one question.
Yeah.
Like, should there be any relation between the QX distribution and the PK?
QX is a completely arbitrary distribution.
So we don't mind whatever it is.
Hold on, I'll tell you. See, look at the measurement process. So let's go back to the measurement process. No matter what distribution QX is, right, the measurement process will end you up in this state. Do you agree?
Yeah.
Similarly, suppose no matter what distribution Q of X is, my magic operation will end me up in this state. Then I claim then the magic operation is exactly identical to the measurement process. It is establishing the same relationship between the classical register and the quantum register. And I claim how much ever information I'm getting from the measurement process, I'm getting exactly the same amount of information about the quantum state from the magic operation. Do you agree?
Yeah. Yes.
Okay, great. So can we simulate the measurement process, right? That's the question. So what I will do the following. So now I will take the following scenario. Alice has this quantum state rho. Okay, so I'll say the following. So scenario one. So I'll say original scenario. Original scenario. So Alice is sitting here. Bob is sitting here. Alice holds the quantum state and she holds the classical register. Okay. Let's say Bob also holds a classical register. Now, so initially, so this is post measurement. So post measurement. Pre-measurement. So this is pre-measurement. And I'll write the post measurement below. So pre-measurement, the state is as follows: Q of K, K, K tensor rho. And post measurement, it is P of K, K, K tensor theta K. Okay. So this is the original scenario. And suppose okay, so maybe I'll do this slightly differently. So I'm going to say, so the classical register is not with Alice. I want initially so I'm going to say rho tensor KK. So this is your K. And I'm going to look at the following. So just one second. row tensor K, Q of K. So this is the post-measurement scenario. Now, pre-measurement scenario, and the post-measurement scenario is, so theta K, and this is K. Okay, now, so now I have theta K tensor KK P of K. And there is a wire here. So the wire has to communicate how many bits. I claim the wire has to have communicate so many number of bits. Do you agree? So Alice performs the measurement, and the outcome of this measurement has to be communicated to Bob through a wire. The quantum state is on the left, and the classical register comes to the right. And I claim that to enable this, you essentially have to send h of pk number of bits to Bob. Do you agree?
So what I'm thinking is you would have, so there is a distribution which is given by trace of rho mk, sorry, mk rho mk diagonal.
Correct.
So the entropy of that random variable would, those many bits you would need.
Correct. Exactly. That's exactly what I am saying. Right. So
Okay.
my distribution h of pk is essentially the entropy of this random variable pk. That is the distribution this.
Okay. PK was that. Okay.
So yeah. So for Bob to figure out the outcome of the random outcome of the measurement, he has to be pumped h of pk number of bits, right? Now suppose I can simulate this. So now there is the original scenario. Now I'll come up with a new scenario. So second simulated scenario, I'll call it simulated scenario. Suppose I can end up with the same. So now, so I start with the same thing. So I'm going to explain this. So I start with the same copy. Paste. So I start with the same thing, but this I'm not going to do a measurement now. I will do some simulated process. Okay, and here the rates are, and I also give, suppose I give them some external bits of randomness. Some C bits of randomness. So C bits completely independent of the quantum state. So what I'm saying, so my pre-measurement situation is exactly as before. Now my new process does something. It takes some external bits of randomness both at the quantum state and the classical register. It communicates R bits from the post-measurement state. It communicates. So Alice will perform a measurement. She will store some bits in her classical register. She will take R bits out of that and give it to Bob. Bob will also get some external bits of randomness. And suppose they can simulate this quantum state post this process, then I claim that the Bob's register has exactly the same information content as if he had done the original measurement. Do you agree?
Sir, sorry, can you repeat again?
Yeah. See, this was my, if I do the measurement, this is what I end up with, right?
Yeah.
So I take some, so Alice does the measurement. She has the classical register with the same distribution as this, and then she will send this out on a wire to Bob. And what is the relationship between the classical register that Bob has and the quantum register that Alice has? It is exactly this. Do you agree?
Yeah.
If she sent it out on a wire, great.
Yeah.
Now, my goal is the following. My goal is to simulate exactly the same classical quantum state. Exactly the same classical quantum state. Alice, instead of now Alice performing the measurement, I will equip both these guys with some external bits of randomness. So Alice is sitting here. She has the quantum state rho. Okay. Bob is sitting here. He has the classical register with him. The pre-measurement is in this state, tensor rho. So there is no relationship between the classical register and the quantum register. Pre-process. Now I will give both of them completely independent and useless. So completely independent of the state and the classical register. Both of them, I'll give them some C bits of common randomness. Okay, it's completely independent. It's like it's useless. Okay, completely useless. I'll give both of them C bits of randomness. Alice will do something with these C bits of randomness and the quantum state. She will do something. She will extract out some classical register. This classical register, instead of being with distribution Q of K, instead of being with distribution PK, right? It has some other distribution and whose entropy is R. Okay, so she does the measurement. She uses the C bits of randomness. She does a measurement on rho. She will end up with a classical register with R bits of randomness and a quantum post-measurement state that is exactly theta k. She will send these R bits out to Bob. Bob will do something with the C bits of randomness he's got and the R bits that Alice sends. And if he ends up with K, and if this post-measurement quantum state and the classical register is exactly of this form, then do you agree that I have essentially simulated the quantum measurement?
Sir, Alice will do a measurement first.
Alice will do something. With this.
Huh.
So Alice has the. So I'm going back exactly to the previous circumstance. So original scenario was like this, right? So we will start with exactly the same scenario. So they start with rho and some k which is completely independent. Okay. Originally what you did a measurement. The measurement gives you this post-measurement quantum state theta k and the classical register k, and you push this classical register out to Bob. That's what you did, correct?
Yeah.
Now, what I will do, instead of doing this, I will give both of them some bits of randomness, some C bits of common randomness, C bits of common bits, okay, some common bits that are flipped randomly, I will give them. And I will give rho. With the C bits of randomness and rho, Alice will do something. I don't know what. She will do something. And she will get out a classical register and a post-measurement quantum state. So she will get theta k, tensor, some alpha k. With some distribution R of k. Let's say she does some other measurement. She does some measurement, she will get an outcome alpha k, and with probability rk, and the quantum state is in exactly theta k. She will send this alpha k to Bob. Bob will use the same C bits of randomness and the alpha k, and if he can come up with exactly k that he would have got had Alice performed the original measurement, then we have essentially simulated the quantum measurement, right? The original measurement, right?
Yeah, but still Alice is performing some measurement.
Some other measurement.
Yeah, ma'am. So like why is it like more useful to do some other measurement
Ha,
instead?
because because alpha k could have a lower entropy, which means that she will require lesser number of bits to send it to Bob, right? So in some sense, this h of pk that was there previously, I have split it into two parts, an r and a c. The c is coming from outside and the r is coming from inside.
Yeah, got it.
Suppose I can do this, then I can somehow, I have ended up simulating the measurement, but I have pulled out, instead of having to send h of pk number of bits, I'm sending a lesser number of bits, r. Do you agree?
Yeah,
And the additional c is coming from outside. You see?
yeah,
If I can do this, then essentially what it is saying is I only need R number of bits to communicate to Bob the outcome of the quantum measurement, because the C bits that are needed were really from outside.
but as we are using the C random bits, like there will be some amount of error between the original and this one, right?
Suppose I ensure that there is no error. So suppose I ensure that after C, the exact quantum state or the exact quantum state that Alice has is theta k. The exact classical register that Bob has is k. And this is with probability pk. Suppose I ensure this. Then are you happy?
Yeah,
If I ensure this, then all that Alice is conveyed to Bob is r bits, not h of pk number of bits, right?
yeah,
So that means the information content of the outcome is not h of pk, it is r, because the rest of the C is like completely useless random noise coming from outside.
yeah.
That's the question. So question is, what is the minimum R I can ensure that I get to this quantum state?
Yeah. So like we are not bothered about how they decide on the C. This one.
No, we are not bothered about how they decide on the C. The C is like random bits coming from outside.
They both have access to the random source.
Both have access to the random source C. C bits of randomness is completely, see, the idea is the following, right? So I'll tell you what is the intuition behind this. See, when you perform this measurement, right, you get the outcome randomly, correct?
Yeah,
When you perform a measurement MK, the outcome is random. Now, I can ask you this question. Did this outcome come from looking at the quantum state, or was it just completely random? I can ask, right? Was it just completely random? So, what if nature is not even looking at the quantum state and is just throwing out a random variable with distribution pk? You don't know whether it is true or not, correct?
yeah,
Because it's random. If this was indeed random, then I should have got all my C bits completely from outside and my R bit should be 0. Do you agree?
yeah.
If the nature was completely looking at the quantum state and there was no randomness at all, there was no external randomness at all, then I should get C equal to 0 and R equal to H of pk, correct?
Yeah.
That's what I'm trying to see. I'm trying to see if I can somehow source this outcome using external bits of randomness that is completely independent of the state. If I can do that, then the information content of the outcome is not h of pk but r, which is h of pk minus some c, correct?
Yes, sir.
That's exactly what I'll answer. Okay, I'm out of time. So what I'll do.
Sorry, I had a question,
Yeah.
about this itself.
Yeah.
So when you write this theta k tensor kk,
Yeah,
so the kk part is with Bob and the theta k is with Alice.
correct.
And that is true in both scenarios, the original and the simulated one.
Correct, exactly. In the original scenario, I had to use a wire of rate h of pk. Now I'm giving both of that some c bits of randomness, and I've reduced the capacity of the wire to r. But I've
Okay, so
ensured that the classical register at Bob and the quantum register at Alice are exactly in the same way as if I had used this h of pk.
okay, so basically Alice has the state row and Bob has the classical register.
Correct.
And in the original thing, whatever Alice measures, the measurement outcome has to be sent to Bob, and you use h of pk, many bits.
Correct.
And now in the second simulated scenario, you want to also send the outcome of Alice's measurement to Bob.
Correct.
And once more, his classical register should end up as it would have in the original scenario.
No, you have to be slightly careful here. In the second scenario, I don't want to send the outcome to Bob. I want to ensure that the quantum state with Alice, post measurement quantum state with Alice, and the classical register with Bob has the same relationship as I would have had if I had done the measurement.
Okay, yes. So that part is a bit unclear to me. Like, okay, that part, can you explain that part?
Yeah, see, I am not going to do the original measurement now. I am not going to get an outcome and send that to Bob. I'm not going to do that. I'm going to do something completely left to me. All that I want is the post measurement quantum state with Alice and the post measurement classical register with Bob to be in exactly the same scenario as it was if I had done the original measurement.
Okay, and when you did the original measurement, even in that case, Alice's theta k was correlated with Bob's k.
Exactly. When I did the original measurement and sent it out across on the wire, my post joint state was in this point. My joint classical and quantum register was in this state. Now also I want to ensure the same thing. I don't want that to change. But what I will change is I will change the process what I do. I will give more resources to myself. I am not going to give any resources that are dependent on the quantum state. I will give myself completely independent source of resources. And I'm going to reduce the capacity of my wire. So how many bits that Alice does some other process. She extracts some classical register value. Now, but this classical register value contains all the information from the quantum state that needs to be pumped out to Bob. The rest of the C is completely independent of the quantum state. So Bob already has that access. It's completely independent of the quantum state. He doesn't need to look at that quantum state. That C is there with him. The C bits of randomness is there with him. Using that C bits of randomness, Alice pulls out something that is more juicy about the quantum state, and she sends out only that juicy part to Bob. Bob will use C and that juicy part to simulate the outcome of the quantum state, outcome of the original measurement. That's the idea.
Oh, and in the second part, Bob's register and Alice's post measurement state has to be exactly equal to this thing in green which you have here.
Exactly. They can do whatever they want. They cannot steal something off the quantum state and give it to Bob. They can't do that. They cannot take some part of the quantum state and give it to Bob. No. They can give themselves any amount of randomness totally independent of the state. They can give themselves complete randomness because finally nature is also giving out something random, right? What guarantee is there that nature is not even looking at the quantum state and giving something out completely at random? Possibly it is. So I will give myself completely independent bits of randomness that is not related to the state at all. That's like, just like noise. I will use that noise and I will try and design a more informative measurement whose outcome has lesser number of bits, and I will give those lesser number of bits to Bob. Bob will use that complete randomness from outside, and these few bits of information that I've given him, and he will do something on those two things, and he'll end up with the K exactly as in the original measurement. That's the idea.
Oh, so here the alpha case. So what you're saying is this. Okay, can you just go a bit
Yeah.
down?
Yeah.
Like in the simulated scenario.
Yeah.
Oh, more down. Yeah. Sorry. This figure. This. Oh, sorry. Little bit up above. Oh, so oh yeah. Here this summation RK theta K tensor. This you have this theta K and K is circled, right?
Yeah.
So you're saying that system, the joint system which you have circled there,
Yeah.
that should be the same as in the original scenario.
Correct.
Okay, that's what you're saying. Okay.
Correct. It's like this, right? You are so far thinking that the measurement process, what the measurement process is doing, the measurement, it is making the measurement, it is looking at the quantum state, it's looking at the quantum state, extracting something and throwing it out. What if nature is not even looking at the quantum state? It is taking some randomness from outside, taking some randomness from the actual measurement outcome, pulling them up together, and then giving you a classical register. Suppose that's what it is doing, then I want to simulate that. I also want to take something that's completely independent of the state. That's the idea.
Okay, so like that's why you require this state to be the same as what you would have had before, right?
Okay, I'll do one thing. I know this is a little bit vague, so I will spend a little bit part of the next class also kind of, I'll explain this slightly differently, and then let's see if it makes it more clear.
No, I mean, I got everything, but this, the joint state of like the post measurement of Alice and Bob's register being equal in both cases, that's what I'm thinking about.
Exactly. That's the most important. If I can ensure that conveying lesser number of bits to Bob without any, fishy information communicated outside. So this wire that goes from Alice to Bob of rate R, beyond that, there is no leakage of information from what Alice sees to Bob. Leakage of information or information about the state, nothing of that should be communicated to Bob from outside. If everything from outside is completely independent of the state, completely independent of the state, completely independent of the measurement process, completely independent of everything that Alice does, if I can give something like that to Bob, so I'm not leaking any information of the quantum state to Bob. He cannot re-simulate the measurement outcome. Neither am I leaking him anything after making the measurement to Bob. No, everything post-measurement is sent only through this wire. Now, if I can use that external C to somehow reduce my R, that means really the information content is not h of pk, it is lesser than h of pk, because whatever is required to simulate the outcome can be sourced from something that's completely independent of the state. That's the idea.
Yeah. I think I get it.
Yeah, what I'll do is, I know Srini, this might seem, Tejas might be getting it because he's read a little bit of the paper that is involved here, but you might be having some more doubts. So I'll spend a little bit more time in the first part, the next class, kind of explaining this in a slightly different way so that it becomes slightly more clear. I know, I mean, the dinner starts at close at 9, so you might have doubts. So what I'll do is I'll stop this and then take some doubts, and I will stop recording and then restart recording. Is that okay?
Yes, sir.
Yeah. So what I'll do is I'll stop